12 lecture instead of a CISC124 lecture to the playlist. So if you're looking at the Friday lecture and thinking this looks weird, it's because it's wrong. So I have to re-record last Friday's lecture, I think. So that one has to be updated. All right, so we were talking about maps in the last lecture. Now remember, a map is like a Python dictionary, except when you use it, the way you use it is very different than the way you use a Python dictionary. All right, so the method put is what you use to put an element, or sorry, a key and a value pair, so an entry, into a map. Right, so here we've got the map of capital cities. Now a map has two types, right? It's got a key type and it's got a value type. So when you're using a map class, when you're using the type and you're specifying the generic types, you have to specify both the key type and the value type. Right? In this example, they're both the same, but you still have to specify both. The put method puts in a key paired with a value. Right? So this is the map of provinces, capital cities mapped to provinces. Right? So our key is the province, and our capital city is our value. Right? So Ontario has the capital city, Toronto, and so on and so on and so on. Now put actually, do I tell you anywhere? No. Put actually returns a value. Right? So put returns null if this key if the key Ontario is not already in the map when we put it in. Right? So when you call put Ontario, Toronto for the first time, that succeeds. It returns null. Now, if you call put again and pass in Ontario as the key, then what put does is it replaces the value with the new value, right? And returns the old value back to the caller. Right? So often when you use put, you're looking at the return value of put to determine whether or not it successfully, to determine whether or not it put a new entry into the map, or if it's replaced an existing value in the map. Right? So keep that in mind when you're using put. Right? So after putting in those 2, 4, 6, 8, 10, after putting in those 10 entries into the map, you end up with the following map. Right? Now remember, a map or a dictionary is just a two-column table, right? Where your first column, these entries are unique, or sorry, these keys are unique, and the values are not necessarily unique. Right? Remember, each row of the table is called an entry or a key value pair. Right? Either one's fine. To get a value from a map, you use the get method. Right? So it's similar to a list where you use get and an index, except in a map you use get with a key. Right? Now, unlike a list, if you call get with a key, and that key is not in the map, you end up getting back the value null, right? Which we haven't really seen yet in this course. So in Java, the word null, or the value null, is a value that you can assign to any reference variable. Right? So for example, I can assign null to this string city. Right? The keyword null means no object. Right? So if you have no object, there's not really much you can do with a null reference. Right? You can't call a method belonging to a null object because there's no object. Right? So if city happens to be null here and you try to do something like city.toUppercase, you end up with an exception. Right? So if you ever see null pointer exception, it's because you're using an object whose reference whose value is null. Right? So if there is no key corresponding to Ontario or equal to Ontario, then you get back null. If there is a key equal to Ontario, then you get back the value that's stored with Ontario. Right? So in this case, you get back Toronto. If you want to know, does the map contain a key, then there's a ContainsKey method. Right? So this returns true or false if the map contains the specified key. Right? So here I'm going to ask, does that map of capital cities, does it contain the key Nunavut? Right? And if it's not, right, so if it doesn't, then I'm going to add Nunavut with its capital city, Iqaluit, to the map. Right? Similarly, we can add Northwest Territories and the Yukon. Right? So there's an example of using ContainsKey. Now remember, ContainsKey you can also use get, right, to achieve the same effect. Right? So we could replace these with if capitals dot get Nunavut equals null. right? And that would be the same thing. Or it would have a similar effect, sorry. Okay, so here's an example of using a map to do something that is occasionally useful. Right? So suppose I have a list of strings. It doesn't have to be strings. It could be anything. Right? So I have a list of stuff. I want to know how many times each element appears in that list. Right? This turns out to be very useful for a lot of different types of problems. Right? So for example, I might want to know what's the most commonly occurring string. I might want to know what's the least commonly occurring string. I might want to know how often does each string appear in the list. If I'm doing some sort of language analysis, for example. Right? Okay, so the way you do this is, so the way you can solve this problem is you can, let me back up a step. So if you had a list of items and you wanted to count how many times each item appeared in the list, and you weren't using a map, then what you would end up doing is you would loop over the elements in the list, right? So for each element in the list, and then you would loop over the list a second time, right? So you'd use a nested loop, right? You would count how many times each element appears in the list, right? So you'd be in an O(n) squared situation there. If you use a map, then what you can do is you can put each word into the map, right? So you look at the first word, put it into the map, right? If it's already there, you just add 1 to the count, right? If it's not already there, you set the count to 1 because you've seen the word for the first time, right? And so it ends up looking something like this, right? So I'm going to make a map, right? My keys are going to be my strings, so the words in the list, and my value is going to be an integer, right? The number of times each word appears in the list, right? So I'm going to call my map count. And now I'm going to loop over the strings in the list. Right? So for each string in the list t, right? If that key is in the map, right? So use ContainsKey to test if the key is in the map, right? Then I know that I can get the count of the number of times that word has appeared already, right? So I use get to get the number of times the word S has appeared has appeared so far, right? And now I put it back into the map, this time adding 1 to the current count, right? And so put overwrites whatever the current value is with n plus 1, right? Now if ContainsKey returns false, then we haven't seen the word yet. So we put the word into the map and we give it a value of 1 to indicate that we've seen the word once. Right? And there's a nice simple way to count the number of times every element appears in a list. Right? That algorithm there runs in O(n) time. Right? There's n elements in the list. ContainsKey is O(1) for a hash map. Get is O(1) for a hash map, and put is O(1) for a hash map. Right? So that's a very fast way to count the number of times something appears in a list. Count the number of times every element appears in the list. Okay, so the keys in a map form a set, right? Because that's the way the map's defined, right? So the keys are unique, therefore they form a set, right? Therefore, it kind of makes sense that you can ask the map for its set of keys, right? And so you can do that. There's a key set method, right? So using that, using the map from the previous slide, right? I can ask the map of counts for its key set. And that'll be the words that are in the list, right? Or the unique words that are in the list, right? And now you can loop over the set using a for each loop, right? So for each string in the set of keys, right, I can do something like get the number of times that word appears, right? So I can ask the map for the current count, right? And then I can do something like print that word occurs that many times in the list in T, yeah, in the list T. Right, or something else, right? So you can process each element of the key set, right? Perhaps getting the value corresponding to the key set. You don't necessarily have to, right? And now you can do something, and then you can perform some computation. Okay, so the values in a map are not necessarily unique, right? So they form some kind of collection, but we don't know what kind of collection. So the map class doesn't tell you what kind of collection. Right, so all you know is that there's some generic collection of values. Now, for our purposes, we can treat that collection as though it were, you can't quite treat it as though it were a list, right? But you can loop over the elements in the collection. Right? So you can ask a map for its collection of values using this method called values. Right? So count.values gives you back this thing called a collection, which we haven't seen yet. I'm going to describe later on in this lecture exactly what a collection is. Right? For the time being, you can just think of it as being something that can hold more than one element, right? Where all the element types are the same. It doesn't have any indexing, right? So you can't use it like a list. But you can write a for each loop over it, right? So I can write a for each loop over that collection of values, right? And now I can count the total number of words that are in the list, right? So the number of strings is just sum up all the values, right? And now I can compute, for example, the average occurrence of each word. Right? So key set and values. They're a bit unusual for us. So let me back up a set here. So when we did a key set here, right, I didn't say hash set or tree set or linked hash set here, right? I said set. Right? Similarly with values, I didn't say array list or linked list or some kind of set. I said collection. Right? So, so these methods here, it turns out they're not returning. What are they to return? It turns out their return type, set and collection, these things are called interfaces in Java. Right? So they're not classes. They're actually these things called interfaces. And we haven't seen, I haven't told you formally what an interface is yet. All right, so what is an interface? So in Java, an interface is a specification, right, but not an implementation of an API. Right? So all that means is that an interface is a bunch of methods, right? But the interface doesn't tell you, or the interface itself does not implement the methods. Right? So the interface says what methods exist, right? It also says what the methods promise to do, right? So you can actually look up the documentation for an interface, and you'll get the contract for the interface methods. Right? But it does not specify how the methods are implemented. Right? So for example, if you go and look at the list interface, right, it says that every list has to provide a get method. Right? It says every list has to provide an add, well, sorry, not exactly. Every list has to provide a size method. Right? It says every list might, list can provide an add method, but it's optional, and a bunch of other stuff. Right? So it's just so an interface is just a list of methods that the interface says must exist. Right? Similarly for set, right? The set interface is just a bunch of methods that specifies what every set must provide. Right? Every method which that every set must provide. Right? So there's an add, there's a get, add, get, contains. All right, so if you have an interface, you have to have a class that implements the interface. Right? So if you have a class that implements an interface, then that means that the class promises to provide every method that's in the interface. So for example, ArrayList provides every method that's in the list interface. Right? TreeSet will provide every method that's in the that's in the set interface, right? And so on and so on and so forth. So interfaces are, in fact, reference types. Right? So they do define a type. Right? And that means you can make a variable or parameter whose type is also an interface. Right? So I can write something like, right, list string t is a new array list. Right? Or map string integer is a new hash map. Right? So I can actually store any kind of list, like array list, in a list variable. I can store any kind of map in a map variable. Right? And so on the left-hand side, we have a type that is an interface. On the right-hand side of the equal sign, right, you've got a class that implements the interface. Right? So what you can't do is you cannot write list T equals new list, right? Because there is no class called list, right? And you can't actually make a big L list object, right? I can make an array list object because array list is a class, but I can't make a list object because list is not a class, right? It's something else. But it's still a type. Okay, so these things, the lists, the sets, and the maps that we've been looking at, these are all part of what Java calls the Java collection framework. Right? So this framework is made up of a bunch of interfaces, namely collection, set, list, map, and a bunch of others. Right? So the interfaces, they define what methods the various types of collections support. Right? Then it's got a bunch of classes, so things like array list, or tree set, or hash map. Right? So the classes implement the interfaces. And there's also a bunch of algorithms. Right? So there's a bunch of classes that have static methods in them, right? That provide algorithms that operate on collections. Right? So for example, the collections interface, the collections class has methods that can sort a list, right? Or count the number of times something appears in a collection, and so on and so on and so forth. Right. All right, so if I were to draw you a picture of this thing called the Java collection framework, it would end up looking something like this. So this is what's called a UML class diagram. So UML stands for Unified Modeling Language. It's a visual language. Do I tell you all this stuff somewhere? No, I don't. Okay, so it's a visual language that's used to describe object-oriented software. Right? It's much more powerful than what I'm showing you here. So what I'm showing you here is an example of a diagram that shows you the organization of the various interfaces in the Java collection framework. So up here we've got a box, right? And then inside this double angled bracket construction is the word interface, and then there's the name of the interface. Right? So this is UML's way of saying that there's an interface called Big C collection. Right? Similarly, there's an interface called Big S set, and one called list, and one called queue, and one called sorted set. These arrows, these open arrows, joining list to collection, right, and set to collection and queue to collection, right? So these open arrows are all saying that list is what's called a sub-interface of collection, right? What that means is that every method that's in collection is also in list, right? Every method that's in every method in collection is also in set, right? And every method in collection is also in this thing called queue, right? And so you can see here that collection, this interface collection, you can think of this as being the, I guess, the root of this inheritance of this hierarchy of interfaces. Right? This thing called sorted set. Right? So it's a sub-interface of set. Right? And so what that means is that it has every method that set has. Right? And by implication, it means that sorted set has every method that collection has. Right? So collection is the interface that has the fewest methods. Right? So it's got a get. It's got, I don't remember what's in it. Get contains, right? Does it have a get? It has a contains, it has an add. It has equals. I guess I should just look it up. So let's just look it up instead of trying to remember what it all is. So Java 8 collection. Okay, so let's look at what's in the collection interface. Okay, so collection has add, it has add all, it has clear, it has contains all, equals, this thing called hash code that we'll look at in a few weeks, and a few others. There's remove, right? So it has, and there's size, right? So it's got a bunch of methods that we've seen in the list and set interfaces, right? Now if you go to the top of the documentation, you can find its sub-interfaces. Right? So all known sub-interfaces, right? So there's something called list, right? There's something called queue, there's something called set, there's sorted set, there's navigable set, and there's a bunch of other stuff that are also sub-interfaces of collection, right? If you click on list, right, you can see all of the list methods, right? So add clear equals get by index, right? And so on and so on and so forth. If you look at the documentation again, you'll see the section called all known implementing classes. So these are the classes that are part of the standard library that actually implement the list interface. And you can see there's a bunch of them, right? So I told you about array list, and I mentioned linked list, but it looks like there's a bunch of other types of lists that you have access to. And similarly, if you go back and look at the set interface, right, you'll see that what type of sets do you have? Well, you've got a tree set, you've got linked hash set, you've got hash set, but it looks like there's other sets as well that you also have access to. Okay, so I guess the next set of slides describes what I just told you, right? So everything in red, those interfaces include all the methods that are in collection, right? Sorted set includes all of the methods that are in set. Oh, sorted set, by the way, is the interface that tree set implements, right? Hash set implements the set interface, right? So hash set is not a sorted set, right? But tree set is a sorted set. The map classes, the map interfaces, they form their own set of interfaces. So a map is not a big C collection, right? And if you go back and look at the collection interface, you realize very quickly why it's not. Right, so if we go back and look at the collection interface, right, you see that every collection, right, possibly has an add method where you can add an element to the collection, right? But that's not the way a map works, right? To add something to a map, you need a key and a value, right? So it doesn't make sense that maps are also collections, right? Because the things that you do with a map are fundamentally different than the things you do with a list or set. Right? So map forms its own interface, and then there's another interface below map called sorted map, right? So tree map implements the sorted map interface, right? Hash map implements the map interface. Okay, so a collection represents a group of objects where each object is called an element of the collection, right? So this is the most general. This is the most general type of. This interface defines the most general methods that operate on collections, right? And so this actually lists most of them. This lists the ones that are relevant to us anyway, right? So you can see that every collection has some basic operations, some bulk operations, and some array operations, right? So basic operations are the ones that operate with normally a single element. Bulk operations operate on multiple elements, right? So I can ask, does a collection contain everything in another collection? That sounds useful, right? I can ask a collection to add everything from another collection, right? I can ask a collection to remove everything from another collection, and I can ask a collection to retain everything from another collection, right? So a list is a collection that holds its elements in a numbered sequence, right? Which we've seen already, right? So when you use a list, you use an integer index to access the elements, right? So list supports positional access or modification, right? So you can manipulate an element based on a numerical index, right? You can search a list, but that kind of makes sense because you can search a collection, right? So there's a contains method and there's a contains all method in collection. So it's not surprising that list also has a contains method, right? Lists, you can iterate over elements in a list, but you can also iterate over elements in a collection, right? So this means that you can write a for each loop over any type of list, any type of collection, which means you can write a for each loop over any type of list or set, right? And then there are these things called range view operations, which I'll explain in just a second, right? So now list adds a bunch of interfaces to a collection, right? So notice the syntax up here, right? So the keyword interface appears instead of class, right? And now for the list interface, it says it extends the collection interface, right? So when you see this extends something, all that means is that everything that's in collection is also in list, right? So even though the methods in collection aren't listed here, right? All of those methods, right, that are part of collection also belong to list, right? And you don't repeat them in the list interface, right? So the list adds a bunch of operations that are different than the ones that are in collection, right? So I can get an element or set an element by index, right? We can add an element by index, and you can remove an element by index, right? It adds additional methods for searching the list, right? So there's an index of and a last index of, right? Why is there no index of for collections? Because collections, they don't model, collections don't have an integer index, right? That's not the abstraction that they try to, that they're trying to represent. That range view is the sublist method, right? So by range view, it means you can get part of the list. And the method that does that is called sublist. So set is the collection that doesn't contain duplicate elements, right? The interesting thing about set is that it only contains the methods that are in collection, right? And then it changes the way that those methods behave, right? So it adds the restriction that you can't put duplicate elements into the collection, right? So there's no, right? So I'm not showing you the list interface because the list interface is exactly the same as the collection interface. Right? So map is its own type, is its own interface, right? And it also has, so map defines basic operations and bulk operations, right? So the basic operations operate on one key value pair, right? The bulk operations operate potentially on multiple key value pairs. Maps also provide access to their key set, right? Their collection of values. And there's this thing called entry set. Public set, yes, the entry set, right? So the entry set is the set of key value pairs, right? So remember I told you a map is just a two-column table, right? So the key set, the entry set, sorry, represents the rows of the table, right? There's a funny name here, right? So the entry set is a set, right? Because the key value pairs are all unique, right? Because the keys are unique. Right? So they form a set, right? The type of element that's in the set, though, is this funny map.entry, right? And each entry comprises a key and a value pair, right? The fact that this is map dot is trying to tell you that this class called entry, or this class. So this class called entry is actually defined inside the map interface, right? So this is an example of a nested class in Java, right? We'll see more of that towards the end of the course, right? But if you're wondering why it says map dot, it's because entry is defined inside the map interface. Oh, actually, it's right here. It's right there, right? So there's the first example of a nested, in this case, it's a nested interface, right? So it's an interface, right, that's defined inside of another interface, right? So similarly, you can define a class that's inside of another class. And we'll see examples of why you might want to do so much later on in the course. Okay, any questions about the collection? Yeah?
So can a subinterface overwrite the method of the parent interface?
Sure can, yes. But we won't get to that until we start talking about inheritance.
So does the contains for a set overwrite the contains for a collection?
Yeah, because sets know how to, because sets can search themselves much faster than a generic collection can search itself. Yes. Okay, moving right along. So I think we're going to start talking about making classes now. So far everything we've done has basically been how to use Java in a procedural way. which isn't the way you're really supposed to use Java. Right? So Java is an object-oriented language, so you really, when you're creating a Java program, often what you're doing is you're making a bunch of classes and interfaces. Right? So now I'm going to show you how do you make a class. Right, so let's start out with some basic terms so that we're all on the same page. Right, so first of all, what is a type? So we've done this already before. Right? So a type is a set of values and the operations that you can perform with those values. Right? So for example, string is a type. Right? What are the values that are strings? Well, anything, any sequence of characters, right, including the empty sequence. Right? What can you do with those values? Well, I can do things like test if two strings are equal. Right? I can get a character at a specific index, and so on, and so on, and so on. Right? List is also a type. Right? So what are the what are the set of values of lists? So any sequence of elements, right? Any sequence of 0 or more elements, those are the values. What can I do with a list? Well, I can test if two lists are equal. You can, in fact, test if two lists are equal. Right? You can test if two sets are equal. You can test if two maps are equal. Right? So two lists are equal if they contain the same elements in the same order. Two sets are equal if they contain the same elements, not necessarily in the same order. Right? Two maps are equal if they contain the same key value pairs, not necessarily in the same order. Right? So the sizes all have to be, so two collections are equal if their sizes, can be equal if their sizes are the same. We know about the primitive types. I'm not even sure why this, primitive, okay. So this is just a review of the types, right? So the primitive types, right? So remember there's 8 primitive types in Java. They begin with a lowercase letter. Most of them are numeric, right? Anything that's not primitive is a reference type, right? And that includes an array, right? Even if the array elements are primitive, right? The array is not, arrays in Java are not primitive types, right? They're reference types. Right? Everything else, so every class or interface is also a reference type. Right? So what's a class? Well, a class is just an implementation of a reference type. Right? So in other words, it's a user-defined type. So for example, string is a class. String is a class and it's a type. Array list is a class and it's also a type. Interfaces are types, they're not classes. Right? So an object is just an instance of a class. Right? So like the number 1 is an instance of an int. Right? An object is an instance of a class. Right? So the string ABC is an instance of a string. Right? How do you make the object or the instance? Right? Well, you use the class. Right? So the class is basically a blueprint that's used to make objects. Right? So for example, when you write new array list, right, the constructor of array list uses the array list class to make an array list object. Oh, sorry. Okay, finally, what is a reference? So a reference is just an identifier that can be used to find a particular object in memory. Right? In many Java implementations, references are literally memory addresses. Right? In Java, any variable whose type is not primitive is a reference, right? Is a reference type. So in this example here, right, I've got a variable called t. I'm assigning an array list object to that. Well, it looks like I'm assigning an array list object to t, right? But what's actually happening is, right, you're assigning a reference to an object in the variable t. Okay, so I'm going to show you this thing called a memory diagram. And this is just a way of thinking about references and primitive types. Right? So a memory diagram, just think of this as a table. It's got 3 columns. Right? Column 1, you've got a variable name. Column 2, you've got a memory address. And column 3, you've got some value. Let me just quickly scroll through. Okay. So the memory addresses, you can just think of them as being an integer index. Right? Starts at 0, goes down to whatever number you want. Right? And so they're sequential. Right? So here I'm starting at 98, going down to some number. Right? inside the box, inside the value box, you're allowed to put one thing, right? Typically, it's one number, right? And that's all you can put in there, right? So I'm allowed to put in a number, or I can put in true or false. I can also put in a label, but the label is not actually, just for clarity, right? So here we've got 3 lines of code, right? So double x equals 1.0, right? So in this memory diagram, somewhere I have a variable called x, right? It doesn't matter where you put it, right? You can't put it into you can't put it into on top of another variable, right? So anywhere that's free in your memory diagram, you can plunk the variable, right? So here I put x, right? Now x is a primitive type, so the value that's stored in memory is the value of the, is the value that you want to store, right? So the value in memory associated with x is minus 1.0. Right? Now t is a reference type, and so is u, right? Their types are both big L list, right? So we write t equals new array list. So what does that do? Well, that makes an array list object somewhere in memory, right? So that array list object appears somewhere, right? It doesn't appear beside t. This is the important part here, okay? So the array list object does not appear beside t. It appears somewhere else, right? So I've just written in array list string object somewhere in memory, right? I don't know what value to write in for this thing, right? Because I don't know what's inside the array list class, right? So somewhere in memory, an array list object appears. The value that's stored in t is the address, so it's the middle column, right? It's the value in the middle column belonging to that, where that array list object is located in memory, right? So I'm always going to use an A after the number to indicate that this is an address, right? So 700A means the address 700, right? And that's to distinguish it from just being a regular plain old int, right? When you write u equals t in Java or in Python, right? Literally what happens is the value that's stored with t, right? So what this means is take whatever the value of t is, so that's 700A, and store that in u, right? So u is also 700A, right? So when you use u to access the list, you're accessing the same list that t refers to, right? In this picture, you've got one list object. You have 2 references to that list, right? If you use either t or u to access the list, say to change it or to do something with it, right? Then the other variable, then when you use the other variable, you see the same changes to the list, right? Because it refers to the same list. All right, any questions about that? Okay, the object model. So in object-oriented programming, not Java, not just Java, right? In the world of object-oriented programming, there's something called the object model, right? So in procedural programming, basically you're focusing on decomposing a program into functions, and you pass data into the functions, right? Somewhere there may be some global variable that represents the data that your program is trying to maintain, right? Or that data could be living in a method somewhere. Function or method, sorry. Object-oriented programming works in a different way, right? So in object-oriented programming, you're focused on decomposing programs into interacting objects, right? Those objects contain the data, and they can operate on their own data, right? Similarly, also objects can communicate with one another, right? So in the object model, there are 4 main elements, right? So there's something called abstraction, something called encapsulation, something called modularity, and something called hierarchy. Okay, so what is abstraction? So this is a quote from one of the people who's I guess is a recognized expert on the object-oriented programming language, on object-oriented programming, sorry. Okay, so abstraction is one of the fundamental ways that we as humans cope with complexity. Right? And abstraction denotes the essential characteristics of an object that distinguish it from all other kinds of objects, right? So notice that part's in red, right? And thus provide crisply defined conceptual boundaries relative to the perspective of the viewer. Right? So what does all that mean? Right? So it denotes the essential characteristics of an object that distinguish it from all other kinds of objects. Right? So when we talk about something like a list, right? List is an abstraction of something, right? So it's an idea of something, right? Right? So what are the essential characteristics of a list? Well, it's a sequence of elements, right? So it's an ordered sequence of elements where you can access the elements using an integer index, right? And that's all you need to know to use a list, right? You don't need to know how is the list implemented, right? And you don't even care how it's implemented for the most part, right? So all the nitty-gritty details of how you actually implement a list, you don't care about, right? So in other words, you ignore all of the complexity that you would have to deal with if you actually cared about how it was implemented, right? You just use the list, right? No, there's a get method, there's a set method, right? You don't care how get works, you don't care how set works, right? And that's nice, right? It's nice not caring how those things work, right? Because you don't have to deal with trying to figure out and implement how those things work until later on in the course when you actually do care about it, right? Similarly, when you print out a number, so when you print an integer or if you print a floating point number, right? I think all of you take it for granted that you can just write print or system.out.println something, right? But if you actually think about how that number is represented on the computer and how you take that thing and output the number that corresponds it to the screen, that's actually hard to do, right? You have to take some binary number, convert it to its decimal format, and then somehow get it onto the screen, right? If you actually had to do all of that, right, we wouldn't get anywhere, right? You'd spend the whole course trying to figure out how to print a number, right? But the fact that you can just call print, well, that's an example of abstraction, right? So abstraction lets us deal with complexity, right? All of the details that all of the low-level details we can often ignore when using a higher-level language, right? And that's why we want to provide objects or classes for our users, right? We can provide a very complicated class that does something really sophisticated, right? And the user doesn't care how it's implemented, right? They just have to know how to read the documentation for the class, and then they can go ahead and use it. Encapsulation. So this is number 2 in the object model, right? So encapsulation is the process of compartmentalizing the elements of an abstraction that constitute its structure and behavior, right? Encapsulation serves to separate the contractual interface of an abstraction and its implementation, right? All this is, so for our purposes, all this is saying is a class has got some methods, right? So a class has got information, right? A class has methods, right? I can group that information and those methods into this thing called a class, right? So that class is, you can think of it as being, you often see this word compartmentalization or capsule, right? So all my data and the methods that operate on the data, they're hiding behind something, right? Or they're grouped together in one place. Right? If I want to operate on that data, I know what methods to use. I just look at the contract for that class, right? The documentation for that class. Okay, modularity is related to encapsulation. Right? So modularity is the act of partitioning a program into individual components, right? So in 121, right, you were told, hey, when you write this program, don't write one big function, split it up into separate functions, right? That's an example of modularity, right? You take a complex program, split it up into smaller pieces, right? So that's one example of modularity. In an object-oriented programming language, classes are also an example of modularity, right? You might have tons and tons and tons of data in your program. If you can split that data over several different classes, right, then there's an example of modularity. So he goes on, although partitioning a program is helpful for this reason, to reduce its complexity to some degree. Although partitioning a program is helpful for this reason, a more powerful justification for partitioning a program is that it creates a number of well-defined documented boundaries within the program. Right? So in 121, when you make separate functions, right, decomposing a problem into separate functions, right, each function, hopefully, you've documented the function and what it does, right? Each function has a well-defined and documented boundary, right? So in other words, every function has parameters parameters, right? And every function returns some values, and those are documented, right? So every class, right, also has a documentation for it. It has a description of what objects of the class can do, right? And all of its methods are also documented, right? Oh, okay. So those are the three. Those are the three of the four aspects of the object model, right? The fourth one is hierarchy, but we'll get to that later in the course. This is a good place to stop before we actually start to talk about how you create a full-fledged Java program. Right. Any questions? All right, see you in a couple of days, I guess? No, see you tomorrow. Right.